All right, so page 646, number 11 first. And these are with electric fields. So number 11 says a positive charge of 3.2 times 10 to the negative 5 coulombs experiences a force of 4.8 newtons to the right. Okay, so it's a positive charge, and it's experiencing a force to the right. And if it's experiencing a force to the right, then the field must also be to the right. How do I know? Because when there's a positive charge that's placed in a field, the force and the field are always in the same direction. And the question wants to know what's the magnitude and direction of the field. So we know E is equal to FQ over Q. How do I know to use this one? Because it says this positive charge is placed in a field. And this is the equation when it's placed in a field. Also helps with the fact that they gave us a force, and this is the only electric field equation we have that has a force in it. Okay, and so you fill in your numbers. It says a force of 4.8 newtons, and it says a charge of 3.2 to the negative 5 coulombs. And when you do this, you should get an E of 150,000, or 1.5 times 10 to the 5 newtons per coulomb, and it has to be to the right because in a positive charge placed in a field, the force in the field go the same way. Number 12, an electric field points due east, okay, with a magnitude of 3.8 times 10 to the 3 newtons per coulomb, and that's east. At a particular location, a charge of negative 5 microcoulombs. So this time my charge is negative. And we know that for a negative charge, the force and the field are going to be in the opposite direction. So this time my field should be west if my force should be west if my field is east. What is the magnitude and direction of the force? So again, E is equal to FQ over Q. So this time FQ is equal to Q times E. So negative 5 times 10 to the negative 6 coulombs times 3.8 times 10 to the third newtons per coulomb. What I get out ends up being a negative 0.019 newtons, and the negative means west. The force in the field should be in the opposite direction when you're placing a negative charge in the field. Number 13, a negative charge. So again, force and field should be in the opposite directions. Of 2.8 times 10 to the negative 6 coulombs experiences an electrostatic force, so FQ, of 0.070 newtons to the right. Means the field should be going to the left because the charge is negative. What is the magnitude and direction of the field? So E is equal to FQ over Q. So negative 0.070 newtons divided, that one's not negative, this one is negative 2.8 times 10 to the negative 6 coulombs. When you do this, you should get an E of negative 25,000, 25,000 newtons per coulomb, where the negative means left, since we called right positive on the force. And the last one on this page, number 14, says a small charged sphere is placed at a point in an electric field that points due west and has a magnitude of 1.6 to the 4. So our E is 1.6 times 10 to the 4 newtons per coulomb west. If you keep reading, it tells us our FQ is the force, electrostatic force that it experiences is 6.4 newtons east. 6.4 newtons east. We have an east and a west. Their field and the force are opposite. This is going to be a negative charge. And it's asking us, what is the magnitude and nature, positive or negative, of the charge? So rearrange for Q, FQ over E. Normally we would call east positive, so 6.4 newtons goes in as a positive. and the 1.6 times 10 to the 4th newtons per coulomb goes in as a negative. When you do this, you get a Q of negative 4 times 10 to the negative 4 coulombs. So the positives and negatives should work out fairly easily for you as long as you understand when it's a negative charge, force and field are opposite, and as long as you put your positives and negatives in to look after directions. All right, flipping over to page 655. I asked you to do number 20, which says calculate the electric field intensity at a point 18 centimeters from the center of a small conducting sphere that has a charge of negative 2.8 microcoulombs. So they're giving us an R that is 18 centimeters. Of course, we'll have to change that. And they're 2 meters. And they're giving us a Q of negative 2.8 microcoulombs. This one is the charge that's creating the field. We're going to use E is equal to KQ over R squared, where the Q is the charge creating the field and the one that has the R in it. So 9 times 10 to the 9th Newton meters squared per coulomb squared times negative 2.8 to the negative 6 coulombs divided by 18 centimeters is 0.18 meters. Don't forget to square it. You are going to get a negative here, 7.778, might be 7 repeating, times 10 to the 5th newtons per coulomb, where the negative means it's going towards the charge, right? Because remember, the field lines around a negative charge point inward. Okay, so when you're dealing with the equation that has the Q from the source, the positive and negatives mean towards the central charge, or towards the source, or away from it. Negative means going towards. I also asked you to do number 21, electric field intensity at a point 0.2 meters. So again, telling us our R, 0.2 meters from a point charge is 2.8 times 10 to the 6 newtons per coulomb. So E is 2.8 times 10 to the 6 newtons per coulomb. Directed towards the charge. So a moment ago we said towards was negative. So that means this is going to be a negative. Okay, and this time it's asking us what's the charge. So rearrange this for Q. So Q will equal R squared times E over K. So 0.2 meters squared, negative 2.8 times 10 to the 6 newtons per coulomb, and K is 9 times 10 to the 9th Newton meters squared per coulomb squared. And you're going to solve for Q, and when you do, you should get negative 1.244 times 10 to the negative 5 coulombs. Okay? All right. I also asked